Right, so the second speaker is Frank Venmans from the London School of Economics, and he's with the Grantham Research Institute on Climate Change there. He's also the president of the Walloon Expert Committee on Climate. Oh, go ahead, Frank.
I'm very happy that Christian preceded me. Whatever he says, has explained is in my model. So here is actually like second part. Now I'm gonna put all these insights in a model, and moreover, I'm gonna try to add a few elements that are quite important in reality. So one point is that, let me see if, so that we're gonna have stranded assets. So emission, we have all these coal-fired power plants, for example, that is gonna affect the transition. Another thing is we have technological change. By abating emissions, we get cheaper photovoltaics and windmills, etc. And then the third element is uncertainty. So we actually don't know the future well, and that should matter in how we think of optimal climate policy. So this is work with Simon Dietz, who is with me at the LSE, and also Emanuele Campiglio, who is at Bologna University. So we're really thinking about optimal policy. So we are actually abstracting from political difficulties other than stranded assets, the engineering obstacles we might face for the world. Yeah. And so we have these three elements that I explained. I'll go through these three elements part by part, because that's the innovative element that we are bringing. So we are the first paper to combine the three. Yeah, I'll go through them one by one. There is a wide literature doing this, so we're not the first. So on stranded assets, there is both work using the deterministic setting, uncertainty. On technological change, there has been work done on optimal patent policy, etc. And there is a literature entirely devoted on climate risk. Two ways of thinking about this. So one is tipping points. So there is like a jump process. At one point there is a disaster, so to say. And another is gradual uncertainty, the Brownian motion we were talking about, but on the climate sensitivity. That's how we will do it in this paper. We have both in this model. So there are a few standard elements where we don't differ from anybody else. So there is going to be two stocks of capital, brown and green, or dirty and green. And we're going to make the assumption, and this is actually not done in most models, we assume that all emissions depend on dirty capital. It means to reduce emissions, you need to get rid of your dirty capital, and there is the inertia coming in. There is the stranded assets that is threatening you or facing you. You can't reduce emissions just by closing doors and things that that are unrelated to capital. For the climate physics, we simplify slightly, but it turns out to be a very good approximation. Temperature is proportional to cumulative emissions. And then quadratic damage multiplier. So we assume that damages are proportional to production, meaning, thanks to Christian, you understand this, beta equal 1. Now we also have shocks. So we also have the fact that in some bad states of disasters, our climate action is actually risk hedging. So in practice, we have a graph with the beta. We're below 1, we're around 0.7. And then we have an abatement cost function that I'll explain later. Good. First new element, the stranding. How do we think about stranding costs? So this is the last Belgian coal-fired power plant. I saw these smokestacks from my window as a kid. It was in my town. I went to visit it. Extremely impressive, like this 10-story large building, and it's huge. And so they tried to convert it to pellets, so that went well at the start, and then something bad happened and it went bankrupt. So this was actually a quite well-functioning installation, and they're now tearing it down. It's a stranded assets. Normally, in better conditions, you could feed in pellets into this kind of installation, but the idea is it's going to be more expensive to retrofit than just putting the pellets there in the first place. And second, we don't have pellets enough for all these worldwide coal-fired power stations, which in Asia have a mean life age of 17 years. So we have built a massive amount of these in the last 2 decades. Good. So now it's not only the coal-fired power plants. Even if you think about steel mills, road networks, gas power plants, many capital is actually generating emissions. So in our calibration, we assume that 7% of world capital actually is related to emissions, and you need to get rid of that capital if you want to avoid emissions. And we assume that these stocks are typically long-lived, 50 years lifetime, so 4% decay rate per year. Good. Now, when you have too much dirty capital, we assume also that getting like repurposing is also an option. Think of these pellets that you would feed into an installation. So we think of the cost function as quadratic. So getting rid of a bit of capital is going to be relatively easy. You repurpose, but at some point you're going to lose 100% of your value. And beyond that, it's going to be you're going to have like extra costs from inertia in the labor market and inertia in financial market and things like that. But actually, the model very rarely goes there. Second element, technological change. So there are two ways in which we think of technological change. One is exogenous. No, let me first explain marginal abatement cost. So what is always at the core of these models is an aggregate marginal abatement cost. These are emissions. These are marginal costs. With zero effort, we have business as usual emissions. There are a few things we can do that are cheap. Insulation sometimes is cheap. Then we have electric cars. Then we have maybe some hydrogen technology, quite expensive. CCS, very expensive here. So the more you do, the more expensive it becomes. Now we're going to think that if this is the view, the static view today, very expensive here to go to zero with the current technologies, at some point in the future, it's going to be cheaper. And so there are two drivers to this. One is exogenous. If we develop batteries for our smartphones, then that is also going to be useful for electric cars in some way. Or if we develop membrane technology for whatever we want to do, at some point hydrogen is going to be useful for hydrogen too. But then there is also endogenous change. So let me first explain. So the exogenous one is the fact that this slope is just a function of time. Now, the endogenous change is driven by the cumulative abatement over time. Whenever you double your cumulative abatement, there is like a percentage reduction in the cost, and this for every 1% increase in cumulative abatement, you reduce your slope by 0.1%. Good. This is now, how do we get the values? So we take the point of view, we want to get values that are consensus values. And so we fit this regression together with the stranding asset costs to 130 scenarios. That's probably explained in the next slide. 134 scenarios of the IPCC report and the NGFS report. So these are like the main bottom-up models in the world, and we try to get the parameters from these models by fitting with a generalized method of moments. We both try to emulate the total abatement cost, the marginal abatement cost, and that's how we get the values. So our abatement cost structure somehow represents consensus of the 1.5 IPCC report, a bit old by now, a few years old, but that's how we do it. Good. Uncertainty all over the place. So economic uncertainty, both capitals have a correlated Brownian motions. One sad thing about Brownian motions is that shocks are uncorrelated. So that is actually in future work, I want to a process where shocks have correlation, because if we really think far in the future, you would have this good institutional setup, like big growth. It's going to give you big growth for many years in a row, or the inverse, like collapse, you would have low growth in a row, and the shocks are not correlated. But for now, very standard, we have Brownian motions, and then we have the disasters. So every 50 years, there is like a disaster, World War I. So this is fitted on observed data by Barrow, very interesting paper, 2009. Mainly wars and very deep crisis. COVID would be also one. So every 50 year, more or less, you get a reduction of 20% of your GDP. Now, climate. So we assume, actually, it's very hard to put data on climate disasters. So one element is tipping points, physical tipping points, but they tend to come very late. The way we do it, we say, if you have a warming world, if there is 2 degrees, these disasters that we have, and actually they're very much related to conflict, they're going to be slightly worse. Instead of 20% of GDP, they will take 21% at 2 or 3 degrees. And so that is how we get disasters. And then there is a Brownian motion on the climate sensitivity. It's fitted to the data. One only element where I would say I'm slightly different from Christian is that we have slightly higher risk aversion than intertemporal inequality aversion. Yeah, not necessarily ethically defensible. I like the standard sensitivity model, but this is actually quite standard now in risk models for the climate. So we add a bit extra risk aversion. Good. Important, recursive optimization. So I'm not saying, like, okay, we're going to decide today on a path, and once we've decided on the path, we can't change. So each year, the policymaker learns about what's happening and which disasters is happening, and then adapts optimally to the shocks that he observes. So, and the policymaker anticipates this flexibility and so maximizes welfare over the indefinite future. It's very hard technically to solve these models, very big pain. Don't maybe try to do it. It takes a lot of tinkering for years. Good, so results. Let's concentrate on the cost-benefit line. So that's the red line. We start with emissions. So although we have stranded asset costs, the model obviously wants to strand assets. So we want to strand assets. No stranding of assets is a bad idea. So we go down quickly and then reach 0 emissions at the end of the century. So by 2040, we've already reduced by 70% or so our emissions. It's optimal to go down fast. That gives you then 1.7 temperature on average, but also like in the 90 percentile uncertainty interval, you go up to 2.2 degrees. This result depends a lot on how you think about the damage function and the discount rate. So this is, yeah, consensus estimates, but actually there is no big consensus. But so it gives you an idea of which kind of future we're modeling. Then the carbon price starts at 140, and I'll come back to this. Now here the stranding. So we strand $350 billion per year, 2% of dirty capital each year. So the interval under the integral under this is more or less 17% of dirty capital should be stranded before end of life. That is, I would say, reasonable, but it's not zero. No, like don't try to avoid stranding. If you want to stay below 1.5, this is going to be more. I'll come back to that. Now, for the carbon price, I'm gonna. I'll explain more about the carbon price in the next slide. First, this. So the question now is, what does it mean? What is the effect of having these extra elements that we add compared to a standard approach, like in the DICE model, for example? So if there is no inertia in your model, let's say differently, the fact that we add inertia to the model gives us a slightly higher temperature because we have this difficulty in getting emissions down rapidly, and we increase the carbon price initially by 3%, not that much. It's mainly hard at the start, but in the steady state, you're not that much affected by inertia. Then learning. So if there is no learning, if you think of the world as the static costs we face today, and that you would ignore the fact that these costs go down, then the optimal temperature is much higher. So adding this decrease of cost over time reduces the optimal temperature, and the effect on carbon price, though, today is very small. That is because when you have endogenous change, you have an incentive to abate early, because then you also have this cheaper abatement technology earlier. On the other hand, the model anticipates this easy future where technology is cheap, so that is an argument to start with a lower carbon price. Both are more or less compensating each other, so and the latter dominates. You reduce slightly the carbon price. Then uncertainty. So uncertainty is a large argument for carbon, for abatement, for strong action. So by adding the uncertainty, we reduce the optimal carbon long-term temperature by 0.3 degrees. We increase the carbon price by 33%. And it is mainly driven by the fact that we now assume that these wars or whatever disasters there are slightly related to climate or slightly likelier to happen in a hot world. Now, what is the interaction of all this? So what is the effect of adding the three elements? We get a lower long-term temperature, 0.3 degrees lower, and we want a carbon price that is 32% higher. Okay. Now, last element. We also show that actually the carbon price path is affected by these elements. So we argue that in many of the simpler models, the carbon price increases too fast. So meaning starts too low and goes too high at the end. So actually you don't want a carbon price that goes super fast. You want to start high in a welfare maximizing approach. So you want to start high because there is this inertia of dirty capital that shifts the price path less steep. Cost benefit is also reducing, giving you a flatter carbon price, because by having cost benefit, we care about the timing of the damages. And so doing that, you want to, you have this extra return on abating early, that you avoid damages, you have less damages in the remaining time. So most models do only cost effectiveness. They minimize the cost to go to a temperature target, and that makes you indifferent to the timing of the damages. And third point, if you have endogenous change, you have this extra incentive of early action, because it makes you the remaining technology cheaper for the future. So just to put recall a few of the numbers. So you want to strand dirty capital, $0.5 trillion per year. That's more or less 2% of initial dirty assets. And in total, you'll strand more or less 17. That's cost benefit, giving you a reasonable probability to stay below 2. Now, if you do cost benefit and you wait a bit, so you start in 2030, what's more or less in the Paris Agreement now, if you look at these plans of countries, so then you would need to strand quite a bit more. You're going to strand 28% of initial dirty assets. Since it's cost benefit, by then it's optimal to warm the world more, given these extra costs. And you can also say we're going to go for 1.5 degrees. Then you need to strand, in the end, the total stranding would be 40% of your dirty capital. That's it. Thank you for your attention. I hope I'm in the time frame.
Yes, thanks very much. So how much time? Okay. Question?
I've been extremely
so clear that...
or understandable, yeah.
Yes, a simple question, because it's always easy to say, okay, you should extend your model. But the question is, what about North and South? Because you may say, who is going to pay? Are you going to pay proportionally? So at least 2 regions, North and South. And what would you say in this case?
So I'm thinking about optimality. What is optimal? We have this carbon price. How do you think about this carbon? What is actually, so the carbon price in the model is actually the marginal abatement cost. So since this model wants to maximize welfare, it implies that at each point in time, you do the cheapest stuff. But you take also into account that some technologies have a learning rate, and you add this learning return to your policy mix. So what is best is to close these coal-fired power plants, which are mainly in the south, and to pay. So this model doesn't say much. So it's a representative agent. So we don't model the inequality within time frames. We only have inequality over generations. So what this model, what I could add to it by knowing that the world is unequal, you want to have a single carbon price or a single marginal abatement cost at each time, slightly adapted to learning rates of different technologies. And then for all your inequality, you do lump sum. So ideally, you do lump sum. And if we don't do that, it's going to be extremely expensive. And it's not going to be completely politically infeasible. 80% of the emissions are in the global south. What we do in Europe and in the US has almost no effect in the big scheme of things on where we end at the end of the century. We have a huge responsibility on getting the technology and doing our own homework. But in the big scheme, by the sheer small number of people we are, and we will be in the future, 80% and then 85% further down in 1 decade of the emissions are in the South. So this is actually prescribing a marginal abatement cost for everybody, including the South. If we don't apply to the South, we're doubling the cost easily. Inequality is very important. So we need a lump sum. We need all the diplomatic machinery and get this, but we have to think about driving down emissions in the South. And I think the fact that we're now pushing for batteries and electric cars and also notably the photovoltaics and the wind reduction in costs by pushing here in Europe and in the US and in Japan, that is one of the best things that could happen in the sense that they'll have like a large effect in the South. Because now it doesn't make sense to add much more coal. No. Anyway, these technologies have, wind and solar have now become accessible in the South, where 80%, not 90, 80% of the emissions happen.
Thank you. Could you elaborate a bit more on how much, basically, including all these new features, flatten the marginal price path? In the sense that, because that's often when we discuss the rate at which optimally the carbon price should evolve, you tend to say, okay, at the rate of discount, more or less, and voila. And even if inertia is mentioned of endogenous technological change is mentioned, often it's, oh yeah, but it's so difficult to calibrate and to empirically that it's difficult to give a number on how much or how it should impact that rate of evolution. Here you seem to have numbers, and so it would be interesting to learn more about those.
So I'll publish this weekend a paper exactly on that question. So what we find in that other paper, which is really, so everything else equal, we go to 1.5 degree at the end of the century. You want to reduce the compared to the hoteling part by 1% initially, in 2030 by 0.5%, and then by 2040, 0.3%. That is, and that will, more or less, instead of, you would be at 100, and then now you increase to 120, 130. So you start, it's not like a huge difference, but given all the uncertainty we have, I would argue, let's put the dynamics right on things we know. Like damages earlier are worse than damages later.